we are discussing cache memory organization. We have seen how the implementations of the cache memory can be done by means of the direct mapping. There are some advantages because this direct mapping is simple and therefore inexpensive, but there are some disadvantage also, since that the direct mapping being many to one, therefore which means that many memory locations may be mapped into one line of cache. There may be contentions and the hit ratio may fall. Okay, that the miss ratio may increase. Now, this is what has been summarized in these two statements. That advantage is simple and inexpensive to implement. Disadvantage is that fixed cache location for any block, and therefore the contention may increase. Let us see what can be other mapping. Here it is, we have shown an associative mapping. Okay, in this case, that this 24-bit address once more is divided into two. Okay, here this turns out to be the byte address from 2 to 23. That means this 22-bit gives the word address or the block address. Just one clarifications over here, that this 24-bit or 22-bit that or the cache size that we are talking about are essentially for, as an example, naturally in practical implementations, the sizes will vary, will depend upon the system. The address of the total address may be much higher, the cache may be also much higher, okay, or cache may be lower also, right? Now, let's see, in this case, what happens is, in the case of an associative mapping, that this entire thing from 2 to 23, that means this 22-bit is taken as a tag, right? Therefore, say if this be the cache, right, the main memory's content, that or the content of that block whose address is given by this tag is kept in this cache memory, and the total address of the word, okay, the address of the word, that is B, is kept as a tag. This way, that a particular block has to be mapped in a particular line of the cache. That's restriction goes. That means any line can contain the address of any block and the content of any block. And we can keep once more the cache to be much low compared to the main memory size. Say here it may be once more that 16 kiloword. Okay. Now, when let us see how this associative mapping works. When the CPU throws this address, either the address of an instruction or the address of a data, this 22-bit address is brought to a comparator, and the content of this tag field of that cache, where the addresses of the block of whose data is here has been kept, are all parallelly compared. For example, say this is compared, this comes over here, all these content of the tag portion, tag field of the cache memory is brought into that comparator and is compared parallelly. Now, if any one of these tag fields turns out to be equal to the tag field of the address thrown by the CPU, then it is a hit, which means that particular block's address exists here and therefore its content exists, and that content can be taken out of that cache memory. Now, how do you take out the content of the cache memory? Because how will you know that which particular content has been matched with the content of this address? That is, to decide that, naturally the address portion of that cache for this particular, all these particular lines also should come into that comparator, and whose tag field matches with the tag field of the address, that address is outputted here along with the hit being high, okay, hit flag being high. That address is now used to take the content of that particular line of the cache memory. This is called content addressable memory or associative memory, and therefore we call it is associative mapping. Let me repeat once more that this is content addressable memory. That means the address is found out by the content of particular memory location. The content is taken. If it is matches with the stack field, then the address is found out, and content of that particular address is taken out as our expected data. Okay. This is associative memory or the content addressable memory, and that is why it is called associative mapping. You can very easily see, since this has to be done parallelly to make it fast, okay, the total cost of this associative mapping is pretty high, but the disadvantage of the direct mapping, okay, that goes. And if it is miss instead of a hit, actually the action that has to be taken is that it has to go to the main memory to fetch the content of that word. Okay, that word is fetched, that particular address of the block is also taken. One of the lines from here, the content of the lines from here is removed, and the newly fetched data and the newly fetched address is loaded into that line, and the newly fetched data is also set to the CPU for carrying on the activity, which means that there should be some method, okay, some procedure, some algorithm to find out amongst the different lines of the cache which particular line has to be selected, okay, and whose content should replace the new content. That means whose tag field should replace the tag field, and whose data field should replace the data field of the recently fetched address, okay, if there is a miss. Now there are several algorithms for this. We call them replacement algorithm. Okay, for direct mapping, there is no choice, this replacement algorithm. Okay, for associative mapping, these are the different choices that you have. Okay, these three depends upon the use of a particular line in the cache, but this is random. The first one we call it least recently used, or LRU. That means that it is basically a replacement algorithm. Therefore, that line of the cache, okay, will be replaced by the new content which has not been used recently at all, or rather you can say which has been used quite long back. Now, how do you detect? How do you find out that which particular line has not been used recently? For that, what we possibly can do is that keep a time tag with every line and start comparing the present time with the time that is tagged up with every line, and which has the lowest time, that particular line is taken and thrown out. But you see that this is quite a huge procedure and time consuming procedure and very costly procedure which cannot be done. The total replacement algorithm has to be very fast and therefore has to be implemented by means of the hardware only. Therefore, the concept and the implementation involved should be pretty simple so that it can be implemented very fast by means of hardware. Otherwise, the advantage that we get due to the use of the cache memory, that advantage will be nullified. So what is done actually to implement LRU is that corresponding to every line of the cache, one bit is kept here. Okay, but one bit is kept. That one bit tells that whether that one bit is reset to 0 when a new line has been fetched. Now, the moment it is accessed once more, that bit is set to 1. Now, when a line has to be replaced, the hardware checks that which line has a 0 bit. If that 0 bit, the line has a 0 bit, that means that particular line has not been used for quite some time and therefore is a candidate for replacement. Therefore, it replaces that particular line where that use bit is 0, which means since this bit has not turned out to be 1 for quite some time, therefore we can assume that it has been used some time back, has not been used recently, and therefore is a candidate for replacement. This is the least recently used algorithm and implementation. Another is naturally that it can be FIFO, that is first in, first out. In such case, the line which has come first can be is a candidate for replacement. Now, once more, you see that a timer can be kept and it can be compared that with the time that which has come first, but once more it is too time consuming, and therefore what can be done is that hardware wise a circular list can be kept amongst these lines with the header and the tail, okay, as a FIFO list, and the line that is at the header that can be removed being the line that has come as fast, okay, amongst all the lines over here. That is what is the FIFO algorithm. Another is the least frequently used. For least frequently used, every line will have to keep a counter, and the counter has to be incremented every time that line is accessed, and the line that is accessed least number of time has to be removed. And once more you see that hardware wise it is pretty costly and it is time consuming. Therefore, amongst this algorithm, which is based on the use of a particular line of cache, least recently used is possibly more frequently used, and the algorithm that is based on random selection, which does not depend upon the use of particular line, that is also sometimes used. Okay, that means you just at random you choose a line, throughout the content of it, and put the content of the newly fetched word into that line. That's a random algorithm, and it has been seen experimentally that if you use a random algorithm, the performance doesn't degrade much. That means it is quite okay that if one uses a random algorithm for replacement. Okay, that means you randomly choose a line for replacement. Now, this is what we call the associative mapping, and this is what its advantages and disadvantages is. The advantage is that any block can come into any line. Disadvantage is that it's pretty costly. Okay. Now, so long that we have discussed, we have taken only, you can see that temporal locality. That means that if a particular block is accessed in the main memory, it is chances are pretty high that it will be accessed soon. We have not taken care of the spatial locality, meaning thereby if a block has been accessed, the block nearby can also be accessed in pretty short time. Okay. To take care of the spatial locality, we can think of an arrangement here. Here you see that not only that we're talking about a block which is consists of 4 bytes, we are talking of a block which is consists of 4 such higher block which consists of 4 such blocks. That means that we are thinking in terms of 4 blocks, each of say 4 byte size. Okay, this is one block, this is second block, this is third block, this is fourth block, consecutive block. Okay, therefore these 2 bits determine which block it is, and this 2 bit determines that which byte within this block, memory block, okay, we are right at this moment addressing. Now, therefore, the index here is immediately 12 bits, okay, and that 12-bit address, say this is a cache memory, that 12-bit address is a line in the cache memory which is of size 4K of 4 blocks, 4K size of 4 blocks. Here also we have kept a valid bit, okay, these are all, and this is the tag. Let us see, therefore let us mark it. This is our valid bit, this is the tag, and these are the contents of the 4 consecutive blocks that is simultaneously fetched and kept here. Now therefore whenever a hit takes place, so for example the hit takes place this way, that we get that line address of the line from that index bits, this 12 bit, we take the content of the tag bit, right, the content of the tag field of the CPU address is taken, these two are compared, this logic decides, and the valid bit also is an input to this logic. This logic decides that if this is equal and this valid is 1, then it is a hit, and if it is a hit, then that particular word which is addressed by these 2 bits, okay, here, which is addressed by these 2 bits, is taken out through this mux. That means all that inputs to the mux are all the 4 bits. Which particular block will be outputted, that depends upon what is the block address, okay, that means which particular block of these 4 blocks is being addressed right now, that is the input to that mux. That controls that which of these 4 lines will come out as the word or the block, okay. And now if it's a miss, once more the same has to be done. That means the CPU has to go to the main memory, fetch 4 consecutive words, replace them in that memory location. Let us assume here also that we are using a direct mapping, the memory location, the line in the cache, okay, and the CPU then takes that word or the byte with which the CPU will work, and the CPU goes ahead, okay. That's the penalty that has to be paid, okay, if it's a miss. Now this takes care of the spatial locality, because you see that if any of these words is accessed at any instant of time, the nearby words, it is assumed that it will be accessed pretty soon, and once we fetch therefore a particular word, we fetch the words which are nearby also, and therefore expecting that our hit ratio will increase that way, okay. Now this is, whatever we have shown is essentially the direct mapping that we have shown. We can use this for associative mapping also. That means this kind of arrangement can also be used, where instead of 1 block we keep 4 blocks, okay, and in that case we call it a set associative mapping, right, that set associative mapping. Now the question therefore naturally arises that how much should be the total block size that should be transferred between the main memory and the cache memory to have a good efficiency. We'll come to that discussion a bit later, okay. Now one more thing I say, that though I have shown a mux here to choose a particular word within this 4-word block, you see that since these 2 bits gives offset, okay, that offset can be used directly to address a word instead of using a mux also. Now before we come to that what should be the size of a block, let us discuss another point, and what should be the write policy. Now, this arises because of the fact, for example, say that there's a you have got from the cache, but if it's a write in the cache, okay, that means that if you have written something into the cache, that a line in the cache has been altered, and therefore it should be altered in the main memory also. Otherwise, when this cache is replaced, the main memory will contain an invalid data. Therefore, whenever a cache memory's location is altered, the correspondingly that main memory's corresponding location has to be altered also. And that we called, the way that it's done, we call the write policy. Here we have shown two write policies. One is that write through. Okay, this write through means that whenever you write in the cache, you write in the main memory. Okay, whenever the CPU writes in the cache, it writes in the main memory's corresponding location in the main memory also. But it has the disadvantage that it generates substantial memory traffic and may create a bottleneck itself. Since whenever you are writing in that cache memory, you are writing in the main memory, okay, that total traffic naturally may be substantially high and creating a bottleneck. Another policy can be the write back. Here, what is done is that in that cache, that every line contains a bit which is called that use bit, okay, or the write bit. If that write bit is, if the write bit is 1, okay, if the write bit turns out to the moment that we write something into the cache memory in a line, the corresponding write bit is made 1. Then when this particular line is to be replaced, we check whether that write bit is 1 or not. If this write bit is 1, then that particular line is written back into the main memory. Otherwise, naturally, nothing has to be done so far as writing is concerned. You see, that is why I say that it uses an update bit or the write bit for deciding when to write back. If at the time of replacement we find this update bit is 1, then we decide to write back. Otherwise, we do not write back. Okay. Now let us come to the discussion that we said that we'll have, say, block size. What should be the block size? Here, in our practical example, the example that you have chosen for explanations, we have taken a block size of 4. Here we have shown two graphs, okay, that block size versus the miss rate, okay. Our case, the block size is 4. Now, if and the parameter of these curves is the cache memory size, okay, cache size is the, we took a 16 kilo byte of cache, okay, 16 kilo word, not byte, sorry, it should be 16 kilo so 16 kilo word of cache, right? And the total memory was 16 megabyte or 4 mega word. Okay. Now you see that initially, as the block size, say for example this situation, if the block size increases, so for example from 4 byte, right? If we increase to 16 byte, the miss rate decreases. Okay, it was say slightly higher than 10%. The miss rate decreases. It decreases further if we increases the block size, but the moment we try to increase it further, you see the block size, see the miss rate increases once more. This is more pronounced when we have taken that cache size to be lower, you know, that if the cache size is 1 kilo word, you see the miss rate was somewhere when it's 4 byte was the block size, it was nearly 40%. It decreases quite substantially if the block size is increased, further decreases if the block size is increased to 64 bytes, but increases if the block size is increased to 256 bytes. Okay. Now this means that as block size is increased, initially there are some advantages, but that advantage, the amount of advantage decreases and may be disadvantageous if the block size is increased further. The reason being that the reason being that if the block size increases, large blocks if we take, that it reduces the number of blocks that fits into the cache and may result in the frequent overwriting. You know that since the number of blocks reduces in the cache that the whole cache can hold, okay, then if there is a miss, right, in that case that particular block or the particular block has to be removed immediately. And you see, if the number of blocks is low, the chances that the block won't be found in the cache increases, and therefore the chances that the block has to be thrown out increases, generating a good amount of wastage of time, right? Another is that the spatial locality among the words in a large block decreases. If the block size is taken too high, in that case, the advantage of spatial locality is not there, because a particular byte which is farther off from a particular byte that has now been accessed, that it will be accessed pretty soon, that particular thing may not, that particular characteristics may not be true, because that byte is quite far off and the block size is too high, and therefore the spatial locality among the words in a block decreases, and the cost of a miss increases. That is a very important feature. The cost of a miss increases since larger blocks have to be read and written back. You know, the largest blocks have to be taken from the main memory or written back into the main memory, and therefore the cost of miss increases. Therefore, you see that if we increase the block sizes, there are some advantages initially, but pretty soon the advantages are all gone and the miss rate may start increasing. Okay. This is what, so to say, is the general nature of the curve. Actual curve may be, to determine the actual curve, naturally one has to make a study of these accesses and the misses, okay, and the replacements, and then to come to a curve. But these curves are taken from, the nature of these curves are taken from the actual experiments, and therefore this shows the nature of the behavior as the block size increases. Now, one more thing that should be, two more things, in fact, not one more thing, two more things that we should we should discuss here, and that is that one is a split cache. Okay. Here you see this is a CPU. So this is a cache memory and this is a main memory. Now, almost all contemporary systems, okay, uses these two caches. One you call that instruction cache, one is called the data cache. That means from the main memory, that instructions are brought into this I cache, the data is brought into the D cache, and the CPU takes that instruction from the I cache and data from the D cache, okay, and the entire execution proceed the way that, the mapping can be once more a direct mapping or associative mapping, whatever it is, but two caches are maintained in the case, and we call such situation as a split cache. Now, the second case is the two-level cache. In this case, in the CPU, we have level 1 cache, which is of much faster speed. Okay, naturally you see that it will have the same speed of the registers in the CPU, 1 to 3 nanosecond, right? And therefore it can be on-chip cache, we call it. Okay, that's called that on-chip cache. This level 1 cache. Then we have a level 2 cache consisting of SRAM and then the main memory. Here, the mapping is done between the main memory and the level 2 cache, and another mapping is done from the level 1 cache and the level 2 cache. The mapping can be implemented as it has been described, the CPU first tries to see whether it is in level 1 or not. Okay. Because of the locality once more, the chances are high that it will get in level 1. If not, then it is in level 2 and it searches in the level 2, and if not, then only it gets in the main memory, and the replacement has to be done accordingly. Okay, therefore, if it misses here, something has to be brought from level 2, then level 1 has to be updated. Similarly, if misses here, it is brought from the main memory, then it's brought from the main memory to level 2 and then to level 1. Similarly, some such procedure has to be followed for writing back. Now, this is a two-level cache, and once more, almost all contemporary systems utilizes this two-level cache. Okay, realizes this two-level cache. This is, we call it on-chip cache, and this is an external cache out of the CPU chip. Now, this therefore is more or less the picture of the cache memory organization. Let's come back to our memory hierarchy. You see that our aim had been that to get a memory which is close in speed to the cache and close in capacity to the main memory, by means of the cache memory, we can realize this, the illusion of having very high speed memory with the I should say the actually having a very high capacity memory in reality. Okay. Now, this therefore constitute a memory hierarchy from between that main memory, cache memory, and the CPU registers and the level 1 cache here. Now, if that can happen here, why can't somebody think in terms of such a mapping between the disk and the main memory as well, the disk being a direct access memory device, we can access the disk at random, okay, though the disk is access time is pretty slow, that means 10 to 20 milliseconds. Now, what we can think of in such case is this, that we need not restrict ourselves when we are writing programs or executing program to the size of the main memory only. Okay, we can think as if the memory that we have is of the size of the disk space that we have. What we do here, as we have done in the case of cache memory, the portion of the main memory's content we have downloaded in the cache memory. Similarly, we will download a portion of the program or the data from the disk into the main memory as and when it is necessary. Okay, and if there is any change in that main memory's content, we will write that portion back into the disk memory. That means we will have a mapping between the disk memory and the main memory. That means this sometimes we call the secondary memory. Therefore, mapping between the secondary memory and the main memory. An advantage you can see immediately, it's really fantastic, you know, that we can ultimately have a speed of the cache memory and the size of the disk memory for executing, for compiling, for doing any job. We need not restrict ourselves to the size of the main memory at all, and we can do it pretty fast as the cache provides us, as long as, of course, that the hit ratio we can keep within a reasonable value. Now, and the question, we use the tape as an archive, okay, as a backup for this disk space, okay, as a regular backup. We take it, and whenever we needed any informations which has been backed up, we load the tape and can load that portions into the disk. Therefore, with this total arrangement, that means the level 1 cache here, the CPU registers, the cache here, okay, the external cache here, level 1 cache here, CPU register, the external cache here, the main memory here, the disk here, and the tape here constitute a memory hierarchy, okay, where informations between two levels, consecutive levels, can be transferred back and forth as necessary to have a very high, to have the advantage of getting a very high speed memory with the advantage of having a very large capacity memory. And mapping between the main memory and the disk has a special significance and a special name. We call it virtual memory. By virtual memory, essentially we mean that as if the total memory, main memory that we have is unlimited, essentially as if the main memory is mapped onto the disk and portions of the memory that we need is brought from the disk into is mapped into the main. That way we can have as a picture as if that we have a almost unlimited amount of main memory that we have. As I said that this is a concept of a virtual memory, and we will discuss the virtual memory in detail when we will be discussing the operating systems in later lectures. Now, this total thing that we have shown here is essentially constitute what we call the memory hierarchy. That's all that we wanted to discuss about the memory organization. Thank you.